So we're going to talk about how to work on some of the analysis for Lab A2, constant acceleration motion in one dimension. And by now you should have already collected your data on the spark tape and measured with a meter stick the positions of all of your sparks relative to the first spark, which will be your origin. And so you should have filled in the first 3 columns in your data table. We're going to talk about how you can fill in the remaining 2 columns of your data table. So keep in mind that this lab was set up with constant inclination on your air track, and that constant inclination should lead to a constant acceleration motion. So we're going to assume in what we're doing right now that in fact the acceleration of your cart was a constant value. If the acceleration is constant,
remember that acceleration is defined as change in velocity divided by change in time, which is also the slope of your velocity time graph. If you have an acceleration that's constant, then your VT graph should be a linear shape. So we're going to use that fact to help us finish out this data table. So for example, if this is velocity and this is time, we would expect something like, I'm just going to draw a random line and I'm not going to put numbers on the data, but we would expect a graph with a constant slope. Now let's label some things on this graph. I'm going to pick one particular time right here, and I'm going to call that T N. And that might be the time of spark number N in your data. Because the acceleration is constant, at a later time of the next spark, Tn plus 1, your glider would have a different velocity represented by that point. And at the previous spark, Tn minus 1, it would have this lower velocity. Now, what I want you to notice is that because your VT graph is linear, that velocity at the time Tn is exactly halfway between the velocities at time n minus 1 and time n plus 1. So let's label those velocities on the y-axis. This is the velocity at n minus 1. This is the velocity at n. And this is the velocity at time n plus 1. So since we're going to be dealing with linear VT graphs, we can always use the midpoint formula. And the midpoint formula for a line just says to find the midpoint, we take the average of the 2 points bounding that midpoint. So let's apply that to this V graph. What I'm saying is that the velocity at time n is simply halfway between the velocity at time n, minus 1 and velocity n plus 1. We can add those together. We can divide by 2. And note that Vn is the instantaneous velocity at time n, because it is what the cart's velocity ought to be at that midpoint in time. Now, if that makes sense, we're going to use that to finish our data table. All right. In order to use the data table, though, we have to find a formula for the velocity of your cart in terms of the positions, because it's the positions that we actually measured. So we need to use the definition that the average velocity for any time interval
is the change in position divided by change in time. But what we're going to do is use 2 times n minus 1 and n plus 1. So I'm going to apply our average velocity formula to those particular times. So I'm going to use the position of spark n plus 1 and the position of spark n minus 1, and then divide by the time of spark n plus 1 minus the time of spark n minus 1. That, by definition, is the average velocity for that interval. But because of what we expect on our VT graph, you can see the average velocity
for any time interval on this linear VT graph is also equal to the instantaneous velocity for spark n. And that's what's going to allow us to find our instantaneous velocities. So one more time, we're going to take the spark just before the one we're interested in and the spark just after the one we're interested in. We're going to measure those positions with our meter stick, and then we're going to find the average velocity for that interval. And then you should be able to make an argument using the midpoint formula about why that average velocity in fact is exactly equal to the instantaneous velocity at time n. And it's because we have found the midpoint of a line using our midpoint formula, which is, and I'll just add a note here, this is the formula for an average. It is the average velocity from n minus 1 to n plus 1. Okay, let's go back to our data table. We're going to do an example of what we just talked about. So this is some hypothetical data for the first few sparks. And you can see I've filled in the first 3 columns, measured positions with my meter stick. Now you're not going to be able to determine the instantaneous velocity for spark 0 because we don't have any information about what the, well, there's no position of your glider prior to spark 0. So we would need to know a time prior to spark 0, which we don't. So you can leave these 2 blank. So let's do an example for spark 1, which happened at the time 0.1 seconds. What we're going to find first is the change in position from spark n minus 1, which was this one, spark 0, until spark n plus 1, which is this one, spark 2. So I'm going to take that difference. It is 0.027 meters. I'm just putting the units at the top of my column, and all of the numbers will be in meters. All right. Then, to find the instantaneous velocity, what I need to do is divide. I'll write the formula again. I'm going to again use my average velocity formula, which we proved tells us the instantaneous velocity at spark 1. I'm going to take my delta x, which is 0.027 meters. I'm going to divide by the change in time between those surrounding sparks. That over here you can see is 0.2 seconds. And so that's going to give me, for that particular spark, 0.135 meters per second. All right, so now I've done one data point. I'll do one more. For example, for spark 2, I would need to find the change in position between sparks 1 and 3. Sorry, that's these numbers. Take the difference, and that is 0.0335 minus 0.001. I'm going to put that number in the row for spark 2, which is our spark that was at the midpoint in time between sparks 1 and 3. And that number is 0.0325. And then I'll take the average velocity formula again. I'll divide by delta t, this time between sparks 1 and 3. That, you can check yourself, comes out to be 0.01625. I'll put the units at the top of the
data table, and then that applies to all the numbers. So I hope you see the method. All right, so you can now fill in, you just need to do that same operation on all of your data to fill in these remaining 2 columns. And when you're done, you will have a column for the instantaneous velocity versus time, which then you can graph and see if in fact your data show a linear velocity time graph as we would expect for constant acceleration motion.